Thank you, everyone, for attending today. We're primarily going to be looking at a demonstration of the software. So we'll today see how the Attrimod add-on works and how it can be used to better understand and take rock physics scenario modeling to a wider group of geoscientists. So you should see from this demonstration that insights are gained on elements of the characterization workflow, all the way from subtle seismic horizon interpretation to inversion feasibility work. And that's through the use of this multi-scenario modeling tool. I'm going to make an assumption that there's some familiarity with the Rokdoc rock physics tool set today. Apologies if you're completely new to it, but I think it we'll go at a sensible pace so that you shouldn't get left behind. But again, it's pretty open today. Please during the talk raise your hand and ask questions if you want to see something specific or you have a specific question. So today what we'll talk about is, well, what is Attrimod, and then what the basic workflow is before jumping into the software demonstration. And then afterwards and through the software demonstration on really 3 different applications, you should see that we have reasons to use this tool for exploration, appraisal, and development and redevelopment. And again, summary and questions all throughout the presentation. So Attrimod is a multi 2D seismic forward modeling tool. So if you're familiar with the Rokdoc 2D modeling kit, you're kind of boosting the functionality and the power with Attrimod. So instead of working with one model as you would in a regular 2D session, Attrimod lets the user create hundreds of geological scenarios based on different layer configurations. So if you've made a single model in Rokdoc 2D before, you kind of know that if you want to change the geometry, it is straightforward and simple to do, but you've lost your previous model because you had a single model. So what we've moved to is this kind of matrix or column and row format. And by the way, it's co-developed with a major operator, so we have kind of lots of applied insight on how this could and should be used. So you can build multiple geometries here. And then once the models are constructed, you can apply various rock physics scenarios, zone fills, and derive attributes across these multiple models simultaneously. And the new calculated attributes are really to be used as a database to maximize our understanding of rock property variations during field appraisal, as well as understand and identify areas in the seismic data that might match certain geologic scenarios. So it comes down to, I might have a well that I drilled, but even the near offset area, I don't quite understand what the seismic image might mean. Through this tool, I might try building up a number of geometries to try to reproduce the seismic behavior. By doing that, I might essentially build up a poster that my horizon interpretation team could reference as they're continuing to jump into more detailed aspects of the field. So the general workflow here is that we use some well data or regional information to help populate our model using analogs, measured data, or rock physics library. Our geometric models are going to help us explore spatial variations. So what is our geologist telling us is happening in the area? Can we bring that in to this set of models? We'll populate those geometric models with the well and analog data and generate and analyze synthetic seismic models, develop relationships between the geometry and rock properties, and compare this all at planned well locations. So you can always extract, for example, a planned well from one of these models. We'll discuss kind of the functionality in the demo. But ultimately, we're trying to validate geological scenarios and reduce uncertainty. And by exploring these success and failure scenarios, we're gaining insights on what the seismic might be telling us. So we're really taking asset knowledge to develop better pre-infill drilling geological models. So all of the geometries that we might be dealing with, we might do diligence and model in advance. Ultimately to improve drilling decisions and success rates. All right, so what I'd like to do is show a few examples of this modeling tool. What I'm going to first do is actually construct an example session, and just to show the process. So I'm going to start kind of maybe out of everyone's comfort zone right now. We're going to look at some Permian onshore U.S. data. We're going to look at offshore carbonates and clastics as well in a bit, but we'll start here. So it's some onshore wells in the U.S. To give an idea of what's going on, I have a well viewer. The subtle modeling exercise is, what are the effects of total organic carbon on the seismic signal? Will I be able to chase this kind of attribute or parameter with seismic data? So you can see we have a volume log or a volume set with some rich carbonates in the overburden, into the Bone Spring carbonate, which is much more volume of calcite, and then into this Avalon formation, which is what we're trying to characterize today. So with rock physics models in the Rokdoc library, we've perturbed the TOC log and used the updated TOC to forward model new elastic properties. So this is kind of our common workflow here. We know that at the well, we can see some kind of change in elastic properties due to TOC. And our gather preview is indicating that, yes, we might expect to use pre-stack seismic data to chase some of these effects. But so that gives us kind of that 1D picture of it, but we want to expand this into more geometric modeling. So with that, I'm going to build a new session here. So you'll find in your project viewer under Rokdoc 2D, when you have the license, you have a new Attrimod session. So by opening a new Attrimod session, I can name it. So TOC modeling, set the Z step. I might be making smaller Z steps in this example. So I could go pretty much any depth. My target interval is around 3,500 feet. And here I can plan or act on this later by how many different scenarios I might generate. So I might initially say, okay, I only want to make 4 scenarios. I can set the number of sections to 4 and set the number of traces per section. So how many traces will each model contain? I like to bump it up to 50, or depending on how much dip you have, you might want to avoid aliasing in the model. This will have a world position and a trace step. So you can actually export the entire model as a 3D volume that you could step through in a viewer, in a seismic viewer, to look at all of the models later. So you can actually tie these to the actual world coordinates. You can put multiple wells into the model. You'll see when I accept this that I can assign which trace a given well is modeled at. So again, assuming some familiarity with Rokdoc modeling tools, but we have this maybe familiar looking table here with the addition of multiple sections that you can plan at this point for. So what we have is the option to supply some log data for the initial modeling. So you see I have gamma ray, velocities, density, and porosity. I'm going to add TOC. And I'm going to change my minerals because I know my logs are quartz, calcite, and we'll go with dry clay. If I could choose now if I'm modeling water, oil, gas, or some other fluids in the fluid types list. This one is going to be water and oil. And you can set up some initial logs here as well. So what is my initial dry clay? I can assign V clay log, calcite log, and quartz log as complement or an actual log. So we'll set it as the complement, as well as the saturation water, and the oil will be the complement. So that's just an initial modeling setup, and this will be propagated to the other sections initially. I could additionally select markers to use in the model at this point. Allow for a surface velocity, and we'll get our first model, kind of a blank session at the moment. But you might be used to this kind of view, except now we have these multiple sections here. So this is kind of the Rokdoc 2D view. I can kind of explore the bar up at the top. I might have some session summary, session settings that I'd later review. I could update my well data selection. I could add some volume data or partial stack data if they existed in this geometry. But we're getting to this point where we want to make zones. To make zones, we have to first have some events. We don't have any events yet. So we will add events, and we can add these based off of the marker. So Avalon top, and we'll copy to all of the sections. And let's uncheck Avalon top now, and also add Avalon bottom to all of the sections. So now I have some events to work with on the different panels. My first panel might be maybe just a layer cake. My second panel, I could start making some manipulations to the geometry. Maybe I have some kind of onlapping sequence here. I'm adding nodes and manipulating these nodes. And then when I uncheck an event, I'll have kind of locked in that that event. So if you're used to working in 2D, you're kind of constantly updating a single model, whereas here I might say, well, I have another scenario I want to model. I can right click and add a panel or add another model. So one might build any number of models in this model space, at which point you can choose to make your zones. And when you make your zones, you'll be presented with the zone fills menu. On this zone fills menu, you can decide how you'll populate the zones. So by default, you'll be interpolating your single well data to all of the zones. But by selecting a given fill, I could change that zone fill to something like a rock physics model, a constant, some quantity, anything from our list here. And you might have different zones in the different geometries. So what we'll eventually see in a few minutes here is that I might even model different different sequences depending on my objectives here. So what I'm going to actually do is show you an example of this particular project where we've built up some models already. So I'm going to open a session and I'll open the Attrimod TOC project. It opened on my other window here. And so you see I have a uniform model, a tuning wedge, a cliniform, an on-lap sequence, and there have been some attributes calculated here. So pretty straightforward to calculate the actual thickness of any of these zones. So if I go to measure attribute, I can come in and say, well, I want a thickness looking at the absolute or time thickness and build up the base and the upper and lower events to come up with a thickness attribute. These will come in handy in a bit. In this case, I have we're going to pursue our TOC perturbation with this modeling exercise. So what you have here is a base scenario model where we have a TOC interpolated from the well, and we have a VP, VS, and density also interpolated from the well data. These can just be dragged onto the screen and then dragged off or dragged into the section viewer to push them onto the top view. Mouse over allows me to see all of the attributes at the bottom of the screen. So whatever I've placed onto the screen, I can review and mouse over at the bottom. So in this case, what we have is an initial model where we're using a rock physics model in the reservoir section. So we're using the Wernicke-Chaanoff models, which take advantage of TOC. You get a preview of your model parameters here. If I select an RPM, I can go look at my RPM templates and select the RPM of interest from the template. Then the inputs can be populated by the model itself. So the TOC is going to be the base case. This table is the base case, and TOC right here is currently a zone fill calculator. So the initial state is going to be an interpolation. And if I apply, that will update in the back here. So I'm interpolating the initial model. And so you see my initial TOC here. And the RPM is using that TOC to populate the velocities. So by default, you get a zero incident Zopwitz, but kind of the next benefit I want to talk about is the forward modeling that you're provided with in Attrimod. So in the tools section, you have the option to create synthetics or ray synthetics. If I create ray synthetics, I get the start of a normal synthetic modeling function here, but I have the option to select the offset range, select the ray tracing cutoff angle and the angle increment, and ultimately the angle stack or the angle gather geometry as well. By using this function, you have access to additional modeling tools. So NMO correction, you can explore, what if they would have only used a second order NMO correction. Apply a spherical divergence here, so as well as attenuation. So you have some more complex modeling of forward modeling using this tool. As well as mutes. So you can apply angle mutes that have particular offset or angle mute values, or an actual mute table. So it's kind of a unique element to Attrimod that you have a ray synthetic forward modeler, but you also have the classic synthetic model as well. So I probably want a pre-stack version of my forward model as well. So I'll just make a 0 to 45 degree pre-stack using my default wavelet, and this will be Zopwitz. And so I calculate, and now I have this this pre-stack data set that I've just generated. Once I save this, I've now built that model into the base scenario modeler. So if any perturbations that I make here will also contain a Zopwitz model with 0 to 45 degree offset angle offsets. So what I'm going to do now is perform a perturbation on this base scenario model. What I'll do is right click and create a static scenario model. So I'll call this my initial case. And now I have this a populated static scenario model folder. So I have my initial case, and it's this same model now in this initial folder. That gives me the flexibility to right click in my zones, edit the zone fills, and let's go ahead and change the TOC quantity to a zone fill calculation. So now if I select zone fill calculator, I can say, okay, I'll take TOC, my initial TOC, times my volume of shale log, and make some perturbation to it. So I'll just repopulate this script here. Input for TOC is interpolate, and my function is going to be quantity TOC times, let's say our modeling was 0.5 was one of our models. So I'll cut back the TOC, see if we can find a lower TOC zone. So once I do that, I'll hit OK, and this will recalculate the rock physics model given the new TOC inputs. So I now have updated models here, and the base scenario model is now a new base scenario model. So I'm just going to clean up this view a little bit. And let's actually have a look at the acoustic impedance. Gonna just update the display range as well. Looks like we have a little bit tighter range here. I'll set a session AI range. So all other acoustic impedance volumes will be shown on this scale and with this color bar. So, okay, I have acoustic impedance with less TOC, but my initial model also has an acoustic impedance attribute as well. So I want to look at them at the same time. I'm going to right-click and add a new panel below this panel. So I'll add a new model panel. And now I can drag in my initial acoustic impedance and view the two simultaneously. And so that's acoustic impedance, but of course I can do this with my seismic as well. So we'll look at the 20-degree incident model. And you can see qualitatively that our amplitudes are varying in the two cases. So of course we can do more in-depth analysis of this amplitude variation by looking at attributes. So if I measure pre and partial stack attributes, I can do things like generate angle versus amplitude plots snapped to particular horizons. And each panel can have its own attribute panel as well. So in this way, I can populate AVO plots for key reflectors and perhaps search out the key angle at which the interface is best interpreted. So maybe I have a class 2P AVO anomaly that would disappear in a full stack. So I might use this tool to further analyze the best stack to look for particular interfaces and how that interpretation might vary with different geometries. So we have a question: can you model depth varying properties such as finding upward V shale? Yeah, so you have full access to your calculator and programmer functions here. So you can make a trend, a trend where you have some kind of property changing with depth, and easily take that into the inputs of either your base property model or a number of other kind of built-in workflows that are in Attrimod. So for example, we have in the tools box the rock physics model templates forward modeling tool. So any rock physics model in your library, you also have access to in this modeler. So if I have anything in any model that takes kind of the implication of the finding upward V shale into account, I can call in that RPM and apply it per zone to also generate static scenario models. You additionally have access to the rock property, well, you have Gassman dry rock modeling fluid sub, as well as the rock property perturbation workflow. So this is actually guided workflow that will allow you to perform any number of perturbations. So I'll click it and give you a little preview here, but the process is basically picking the reservoir zone and applying a number of different perturbations to this zone: fluid substitution, V-shale manipulation, porosity, rock physics modeling, and resaturation to any fluid that you'd like to model. So this will additionally generate scenarios that you can save and export. So I wanted to kind of leave this particular model here and take it over to a offshore example. So this is an offshore clastic example where I've already generated a few AVO models. So each of these kind of dipping curves here are an AVO model that we've generated for the oil and brine case. So in this example, we're looking at both thickness variations as well as AVO variations. A number of models here. We have a reservoir in the North Sea, so clastics under a shale, and a few different kind of pinch out scenarios, depending on maybe the overburden shale is pinching out, or some of the lower layers are pinching out. You can see I'm now showing in two-way time the models. So the models are built in TVDSS, and the velocities generated by the model are used to generate the time model. The advantage here also, though, is that with each scenario, I can also supply the velocity model implied by the modeling. So in my initial model, you can see depth conversion base scenario ... I can right click, select displayed depth conversion, and switch it to any other depth conversion from the modeling exercise. So in this case, I have an in situ and a brine and an oil case. And now I'll update the time depth model with the new velocities from the modeling. So you can also see what the implications to your time and ultimately your interpreted thickness is based on the velocity changes from your modeling of fluid substitution. I'm just going to open up the rock property perturbation workflow, as it's kind of better focused in this example because it is a clastic example. So I'm going to select the reservoir and a cutoff set. So I can say I specifically want to model within the sands. So we're going to model only at V shale is less than 40%. I select which part of the model is the V shale. So it will be the base scenario model in this case. And then I can use the next buttons to navigate through the workflow. So I initially am offered to substitute to 100% water. I can pick the mineral set that's calibrated, apply some corrections, and perform dry rock modeling. So at this point, I have my dry rock model. I can QC or manipulate the bounds, QC my Poisson's ratio, and move on to the next step. So I can choose what my final fluids are going to be. I can look at any additional QCs here. And calculate. So that I now have a dry model sitting in the background that I can perform additional changes to. Moving through the workflow, I can model and modify V-shale. Modify V-shale using a calculation or some net to gross modifier. So what you have here is the current net pay implied by your cutoff set, and what percentage would you want to change in the net pay. And so I could add a positive, negative percentage here, and it will tell me what my achieved percentage change in net pay is and the achieved net pay. So this is my process of generating this updated model. So porosity can be modified. Velocity and density via rock physics modeling could be updated. And then a resaturation step at the end of the workflow. So again, this will generate an additional scenario that we can analyze with the function.
And Alan, if I may, there's a question in the Q&A box from Gustri Yan Shah. Can you do Monte Carlo simulation by varying porosity, saturation, V-shale? So the kind of things we were just looking at for sort of multi-realizations of VPVS, rho, and synthetics.
So it's not really going to be a Monte Carlo simulation, although you do have these perturbation workflows as well as the add variability option. So it's not quite a it's not quite a, I would say, well, you're simulating within these correlation bounds. So it's not quite like an automated Monte Carlo simulation that's generating synthetic sections, but you can generate any number of additional kind of variable models. We do have some other tools in Rokdoc. Maybe we can discuss offline about just that, but it's actually kind of traced by a single trace modeling with Monte Carlo simulation. But yeah, thank you. That's an interesting question, and setting up any number of, if you do have an approach to set up some variations on these models, you can always bring those variable models in as logs to generate the same the geometric models, but with different input logs. So, but of course, thousands of iterations might be a stretch in it there. You do have the general classification tools, so Bayesian classification, polygon, AVO analysis, what you might be used to in other parts of Rokdoc. You have access to those tools here as well. What I've been showing has been really log based. So I've been supplying some general parameter and maybe interpolating log data and perturbing given the log properties. I wanted to show a carbonate example as well. This might be presented in more detail in your region at the SEG Japan conference later in the year. But it's kind of a workflow in Attrimod where I'm looking at different different potential sequences in a pre-salt carbonate. What I'm looking at is a salt body that sits on a carbonate reservoir. Sometimes we can see the anhydrite reservoir cap. Sometimes there might be a clay-rich intrusion. Sometimes there's kind of variable thickness of the anhydrite cap, so I might want to model that. And I'm kind of building in a wedge for this demonstration as well. So I'm really filling this in with constant values. So what you're seeing right now is acoustic impedance output from my model. If I go look and edit zone fills at what I've done here, I have this carbonate reservoir where we're looking at using the Bernick-Kachanov model, and we're referencing the constants that we've supplied in the model. So we have porosity, calcite volume. This is the clean calcite example of the reservoir. Water, oil. So this is kind of clean calcite with a water oil mix at 15% porosity. If you highlight the row containing the model, you can again see what the inputs are. So I see that I'm calling in my porosity. I've set these parameters in my RPM template. So I've calibrated this model at the well in advance, and it picks up my calibrations when I select the RPM template. So this is 2D modeling, limestone, and so all of the parameters are saved in there and are populated in the table. So I can very easily update these scenarios. So, you know, currently you're seeing 15% porosity. You know, what if I want to look at 25% porosity? So by updating that porosity field, I can just quickly apply, and I should see an update back here as the model is updated. You might notice that some of these zones are defined by basically they live right under the salt, or they live under the salt, then anhydrite, then carbonate. So I kind of have different zone names here, whether it is depending on the sequence. So my reservoir parameters could change in each of these. So carbonate res with no anhydrite versus carbonate res. These are two zones: carbonate res, no anhydrite. If I populate one of them, I can quickly copy the parameters to the other reservoir sections as well. Okay. So it looks like I'm actually looking at the topmost model, which is acoustic impedance of the water, which is one of my static scenario models. So in this example, I've populated a number of static scenario models. I have 10% clay, 15% porosity, 50% oil. So all these different scenarios, I can quickly test and build up attributes for the different scenarios. So you can see I was playing with a wedge model right here, and so looking at apparent thickness versus true thickness. But my other models are here as well. So I'm going to drop this panel for now. We can look at 3 different scenarios here, and maybe I'll put the Zoprowitz near stack as the topmost model. So we have 15% porosity water filled, 20% dolomite, 15% porosity in the next column, And let's say we'll put a clay contaminated version in the bottom. So these are my different near stack scenarios, and my attribute panel at the bottom is looking at the gradient of the top reflector. So with this single panel, I can look at intercept and gradient of all of these, every single one of these models, and start, diving deeper into the subtleties of the different geometries. And of course, I can activate one of these events and manipulate a given horizon just in real time, and it will automatically update every one of my models. So some interesting points here is in the clay case, we actually lose the bottom of the reservoir as the carbonate becomes more similar to the underburden. Gradient is not very extreme in the clay case, colored by this kind of brownish one. Gradient is the most extreme in the oil case. And tuning is having some effect on this attribute as well. So just a few interesting little details that you might pick up along the way. So we really were looking at create a session, building models, creating synthetics and attributes. Once you've created the synthetics and attributes, the scenario models that you generate are all going to have copies of the synthetics for that various scenario. And then finally, I just want to mention what we might deliver out of these models. So you can always choose to export these any of these attributes. So there's a straightforward export 3D function. You can export the data. You can export the time depth relationship that you might have developed with the ray trace function. So if I've done any work here in the ray trace, I can right click and export the smooth velocity field. You can do that from the data tree. You can right click and plan a well down any given trace. So you can generate a well that has a consistent model. Let's actually plan one. You choose which scenario models are going to be generated, and your well will come with a consistent geometry and consistent properties from your data tree. You have, of course, screen grabs of this matrix of attributes and scenarios. And you also have kind of some of the classic AVO analysis mapping that could be performed as well. So are there any questions right now while we're still in the demo area? The cross plot is also attached to the sections, so you can further kind of dive into subtleties of the data with the cross plotter here as well. Yep, so David is asking, just to clarify, to have different event fills within each section, you need to create separate events and corresponding fills. So if I'm just gonna just show you how that works a little bit here. So I'm gonna kind of manage the space a little bit here. So we're looking at this top section right now. It's the same geometry on each column. So if let's put a synthetic on top. and we'll drop, and we'll make it color just to keep it kind of classic. So if I come into my events and I activate, let's move around the base upper sand. So I've highlighted base upper sand, and I hope you can all see, but there are these little nodes now on the event. So each event fills, each event that has the same top and bottom, each zone that has the same top and bottom is the same same property that you're filling. So if I had an area that had base upper sand sitting on Lista instead of intra-res, then I would have a different fill for that particular zone. But other than that, when I change a property, it will change in every section. These all have the same. These all have the same. These all have the same geometry. So, sorry, they all have the same events but different geometry. So I hope that that's answering your question. Please feel free to clarify if it, ask again if I didn't answer it. Is there any 2D functionality missing, or is this a Rokdoc 2D plus? I don't think there's anything missing. I'll open a 2D on another.
I think everything is there. Do we
Yeah, I
have
think it's all there,
colored
yeah.
inversion, for example, in Rokdoc 2D, and that's also in Attrimod. That was the one that I just had to check myself. And then Attrimod has a few extra bells and whistles, like the ray synthetics and the sort of variable depth time models per session. So I think kind of Rokdoc 2D plus is one way of putting it. The actual license structure with Rokdoc, though, is that Rokdoc 2D is included in the sort of base rock physics package. So, and Attrimod is an add-on to rock physics. So you'll always have Rokdoc 2D access by virtue of also being able to access Attrimod.
Yep, thank you, Fergus. So I think we've hit the end of the software demonstration. Of course, we're happy to actually provide some of these data sets if you're interested as part of your evaluation in seeing a built model already. But yep, so just kind of summarizing the applications here. We're thinking about exploration applications, looking at various stratigraphic model scenarios with analog and existing petrophysical data. Being able to consistently apply these workflow-driven rock physics perturbations is the big advantage here. Running this, trying to stay consistent and running multiple tests on multiple geometries again and again is very, it's difficult to manage some of the more complex 2D sessions. And I think this really fills in the gap there and allows you to get to a different purpose. So, working a single 2D session, I think has a benefit. 2D sessions might be derived from arbitrary 2D seismic lines. That's not quite the intention of Attrimod. This is, although you have similar kind of, I could try to match my seismic horizons exactly here. The intention is really to look at these various geometries in these different columns. So for appraisal, development, and redevelopment, you have the option to extract the traces at planned locations, compare those outputs with the petrophysical and geophysical models that you have. The thickness and net to gross perturbation is I think a key part of that, this comparison here. And the seismic modeling is a big boost here. So better incorporating attenuation and NMO stretch into your synthetic seismic generation is going to kind of give you another angle at trying to understand your amplitudes. And so just to summarize, we have different layer configurations. You have Gassman fluid porosity perturbation, as well as rock physics forward modeling tools. In addition to that, you have your programmer that you might rely on. Petrophysical net to gross modeling with rock physics models as part of the workflow, inbuilt workflows. With the ray synthetics, you can model attenuation, spherical divergence, NMO, and you have that per model depth time conversion to help you better understand the implications of these perturbations on your velocities. So yeah, you can produce a library of attribute responses for all of your models. So really, that's the end of it.